Hello, everyone. Welcome back to SAT Math Question of the Day with Professor Emeritus Seth Chaiken, University of Albany, and Joel, Seth's brother. We're here to hopefully show you how to approach SAT math questions and maybe even other math questions. This is from Khan Academy's free practice that we strongly encourage you to do because the SAT basically told Khan what's on the test, and Khan gives you hundreds of questions related to what's on the test. This is a topic called radicals and rationals. It is one of the 5. Khan gives you 20 practice questions per topic. We're only doing the last 5 hardest. So this is the first one of the last 5 hardest. Seth made a request that he didn't want to do linear equations anymore from what we did yesterday. Oh, by the way, today's Wednesday, but today we're going to do Throwback Thursday, just to confuse everyone, because we're not going to meet tomorrow or Friday. Okay, here we go. Which of the following values is equivalent to the expression above? Aha. Let's see. So I guess we have to annotate, right? Get into this annotation mode. Yeah, there we go. Okay. Yeah. Isn't the best way to do this through so annoying. Isn't the best way to do this through rational exponents? To write 9 to the 100th to the 3rd power, but then 9...
No, to the 1/2 power.
Oh my God. Thank you, Seth. So isn't that 9 to the 50th?
Yeah.
Is 9 to the 50th one of the answers? No, but 9... Hey, what's going on with my screen? I can't write. Isn't 9 3 squared to the 50th? So isn't that 3 to the 100th?
Yeah.
Oh my God. Look at that. I got the answer. So what do you think? Is it better to do it like the way I did it? Or is it better to go through the answers and decide which one is the answer? Or maybe
I like the way you did it.
You like the way? I like the way I did it.
Yeah, you follow your nose. You use the... I could say that you simply employed laws of exponentiation.
Right.
Also and simplify the given expression using laws of exponentiation, and it leads you right to the one form that's correct.
Right. Yeah.
After figuring it out, I looked to see if the other ones are equivalent, and I checked each one and saw that they weren't. But 9 to the 50th that you wrote is it's equivalent to the given value, given expression.
Right.
But it's not one of the choices.
Right.
But the SAT, the nature of SAT questions is that every question was willfully and maliciously designed by the question creator to have so that only one of the choices is correct. Which is a misleading way of teaching people math, because in real life, math problems will have multiple answers. There'll be several. Typically, there'll be several. In real life math questions, there'll often be several answers that make sense, and
but
many different methods, many different ways of figuring out the answers, and also the math problem and applying math is that you can learn about the situation by making mistakes.
Right. Well, that's
problem.
That's hopefully what everyone is doing, studying for the SAT or the ACT.
Well, studying for the SAT. If you're going to really do math, You have to go beyond. Don't do it. You have to go beyond SAT.
That's what we're doing is for stake focus. We're talking about the SAT. Now, one thing we didn't do, which I can't believe we didn't do already, is we really didn't talk substantively about how to do this problem. Really, we didn't. We never really. We just.
Well, I said use the laws for exponentiation.
Yeah,
we could
I
review
know.
what
So
they
we have
are.
to go over those laws.
So let's do it.
So okay, so when you have exponentiation, there are a bunch of laws. The way I view it is follow the laws. They work, and they work under all circumstances, which is really sort of crazy. So if you have x to the a over b power, which is called a rational exponent,
not when the base of the exponentiation is 0.
Exactly, except when x is 0. Except when x is 0, these numbers can be anything.
What's x?
Seth, come on.
X is the base.
X is the base. Okay, when you have something that looks like this, where x is the base and you have a rational exponent, rational meaning is the ratio of two integers. It is a fraction. Okay, fraction, right? Then this is, Seth, can I say defined as? Can I say defined as, or do I have to say equal as?
Oh.
We stumped them.
Well, depends on the direction. Yeah, by definition.
All right. Yeah, we got it by definition today.
Yeah, and please, make it clear that the a over b is the exponent of x.
Yeah, okay, fine. Okay, x, a divided by b. So how about a little example? The example would be x to the 2/3 power. Okay? How about that? Okay, example. Yeah. Now, this is defined as, I love when we use defined as because it goes both ways. This is, I got to get this right, the bth root of x to the a, and also it's equal to the bth root of x, and then that whole thing to the a power, whichever one suits you more fancy. Okay? That is the definition. So what you got here is this is the square root of, right? This is the square root of a number.
Yeah.
Of let's say a circle, right? So this is equal to circle to the half power.
Yeah.
That's what we did here, right? That's exactly what we did here.
Yeah. Okay.
Now,
well, there's another law.
Wait, I haven't done yet. And Seth, I'm not done yet.
Yeah.
And then there's called the power rule, which is x to the a to the bth power is x to the a times b. So example, now that, Seth, is that an equal or a defined? That's an equal, isn't it? That's not a defined as. This one here.
Oh,
is that a 3 or a 2?
Is it?
That's a 2, right? I think so. It has to be a 2, doesn't it? The one here, is that that's an equal to, not a defined as. Okay, so so let's do an example there, right? A cubed to the 5th power is a to the 15th.
Yeah.
Okay, now we use that one here to go from here to here. We use that one because we wrote 9 as 3 squared. You see, we wrote 9 as 3 squared to the 50th, which made not 3 to the 100th power. So those are the two rules. The definition of a rational exponent, you can say fractional exponent, and this thing called the power rule. And then we have the product rule too, but we don't have to. We can do the product rule later. Is that?
Yeah.
Is that what those the two rules you were thinking of?
Yeah.
Yeah. You don't seem very excited.
Well, yeah.
That's the way it is, right? That's the way it is. So you need to know those rules going into the SAT because this was on Khan, and Khan knows. The SAT tells Khan what's going to be on the test.
Yeah.
So you'd have to know how to do this. Yeah. So practice on Khan. You can go to this radicals and rational exponents and do the 15 earlier questions if you want a little more practice on questions that are a little easier.
Yeah.
But it's amazing how the fractional exponent, these exponent works, these things work. It's really sort of amazing how they work. I always say that it's a matter of trust because you can do some really wild things like pi to the negative 2/3 power to the negative 9/3 power. Crazy things, right? So this is pi to the negative 2/3 times to the negative 9/3, which is pi, which is sort of crazy, to the 18th, 18 over 9, positive 18 over 9, right?
Yeah.
Yeah, which is pi squared. So you see, they work. It's great. Even if may not have any intuition on something like this. You may not totally understand what's going on here with the pi to the negative 2 to the negative 9/3 power. Completely weird, but the exponent rules work.
Okay, well, where the rule comes from, the starting point of the rule. See, I'm using red here.
Stuff. Let me give some space. I'm fair. I took up too much space.
Well, see, this helps me give you some clues to how to remember what these rules are.
A good idea, because
coming from the mathematician's act of generalization.
Ooh,
and I'll explain that.
Pretty scary.
So get me some space.
I'll get you a lot of space. What we'll do, though, is just as an example, we'll just redo this question neatly. So while you do your thing. So what is the answer here? 9 to the 100th is the 9 to the 100th to the half power, which is equal to 3. No. Which is equal to 9 to the 50th, which is equal to 3 squared to the 50th, which is equal to 3 to the 100th. Okay, now you have all that white space.
You forgot to put the square root around 9 to the 100th.
You're right. Sorry. Okay, so this is the answer. Now, Seth, here, just because we have to make sure we have the right space for you, how about all this blue, like trapezoid thing is all yours.
Okay, here we go.
Go for it.
So the original idea is that when, let's see, A is a counting number, like 1, 2, 3, etc. Then the exponentiation of x to the a was defined as multiplying x by itself a times, right? And therefore, x to the a raised to the bth power, because from this definition is multiplying x to the a b times.
Very nice.
Right? Yeah. Which is now apply the definition of x to the a. X times x, a times.
Times
and B. Then that same thing is multiplied by x times itself, a times. A lot of these little parenthesis guys, and the total number of parenthesis things multiplied together. Yeah, there's b times. Right?
Right.
From here to here. Now, if you look at this expression, how many x's?
A times b.
How many x's are multiplied? It's a times b. That's the answer.
That's the answer. Yeah, very good.
And so we got the formula that x to the a raised to the bth power. So that's equal to x to the a times b. Right? Now, what mathematicians said was, let this formula be let exponentiation be an operation for which this formula is true even when a and b are not counting numbers, when a and b are any kind of numbers. Right?
Right.
So that's how they derive, and they first derive this what do you call it? What rule do you call this?
Power rule.
The power rule. They derive the power rule from simply counting how many times you multiply x with itself in the result. And then they said, well, exponentiation should behave according to this rule when a and b are numbers that you could multiply, even numbers that are not counting numbers.
Right. So there's a quick question. It's sort of interesting. I'm going to ask Seth. I don't really know the answer. So in order to mathematically use that for rational exponents, like I did, negative 2/9 up to the negative 4/25 or something, what do you have to do technically as a mathematician?
Okay.
Do you have to prove that, or what happens with that?
Let's see. Yeah. So now,
but don't prove it, Seth. Please. Don't.
So how does this make sense? Say if one of these is fractional.
Yeah. Well, just answer my question. Don't do it. Don't actually do it, but just please answer the question. How does a mathematician go about using that, knowing that's true for sure? Do they how did that happen? What do you have to do to know? Don't do it. Don't actually do it, but just what do you do with that?
Well,
how do you know? How do math has?
Well, I have to think about and dredge back into what I had studied about the foundations of the foundations of these things, and at this point I forgot that.
You stumped Seth.
Yeah.
Whoa! Great.
Yeah. So, let me think.
No. It's okay. So we have to move on. So that's so that you know immediately, because we do have to move on. But
one of the again, the general approach that mathematicians use to set up these things is that they'll take a formula that is true for certain kinds of numbers, and then they will check if the operation that the formula on certain kinds of numbers can be extended to an operation with more general kinds of numbers. Certain kinds of numbers being counting numbers, general numbers being integers, and check whether there's a unique and non-contradictory system for defines what the results are.
Okay.
And so in this analysis, this rule is must be shown to be consistent with the rule that Joel stated, that x to a fraction, x to I'll put it this way, 1 over a is the eighth root of x.
Okay, so enough
fear. Actually, so this is consistent with what I wrote. Why? Because if you take the definition of the eighth root of x is the val is whatever number it takes, so that if you raise it to the eighth power, you get x.
Okay.
Now, if you write down x to the 1 over a, okay, and then apply the power rule, raise this to the eighth power, what do you get? Well, the power rule this rule says that that's equal to x raised to the 1 over a times a.
Okay, so why
and the x to the 1 over a times a is, guess what, is x to the first.
Right.
And then and 1 is a counting number. This means x multiplied by itself just one time.
Right.
So that equals x. And so if you set up general exponentiation in such a way that x to the 1 over a is the eighth root of x, then the power rule is consistent.
Wait.
With that definition.
Wait. So you're saying that first comes the power rule, and then from the power rule you fudge the rational exponent thing so that the power rule works.
Yes.
Interesting.
You extend exponentiation by the power rule and show that the right way to define exponentiation to a fraction is what makes the radical rule work.
Interesting.
When combined with the power rule.
That's fascinating. So first comes the power rule, and then comes the definition to force the power rule to work. Cool.
Yes.
Okay.
Yes.
So I just want to finish off with, if you don't mind, with one or two other sort of important points that are practical. Let's say you actually want to do a 3 to the negative 2/3 power, 8, which is a very common problem, 8 to the negative.
Wait. Yes, talk in complete sentences.
Thank you, Seth. Thank you. First of all, let me go smaller. I just want to say that you can do fractional exponents on a calculator if you want to check. Let's say you're on a problem like 8 to the 2/3 power. Okay, and we, using definitions, this is the cube root of 8 squared. So that would be 2 squared is equal to 4. Let's say you want to check on a calculator. You could do this on a calculator. You do 8 with the caret sign, and then 0.666667, which is 2/3. So on a calculator, if you do, I'll switch color. If you do 8 caret 0.666667, or maybe even 8 caret in parentheses 2/3, you'll get a 4. So you can do these. You can check if you're allowed to use a calculator on a test. Maybe even the SAT. Well, the SAT, of course, the digital SAT is all calculator. But we don't know if the calculator has this option of a caret. 8 up to a fractional exponent of 0.6667 will give you 4. You could check on calculators. Okay, and we forgot the negative rule, right? We probably should mention it. X to the negative a is 1 over x to the a. And that, Seth, is that a definition or an equal sign? X to the negative a is 1 over x to the a.
That one, maybe why is x to the minus 1 over x? That's because if you do it twice, x to the minus 1 raised to the minus 1, you get x back.
Right. So, okay, big question. Is it an equal sign or a defined as? What do you think? Or is it too philosophical for us to even care about? What do you think? What do you want to
see? It's a consequence of...
Yeah.
There's another rule that we didn't mention. You right. said we won't do it.
Yeah. Okay. Why not?
Yeah, I think the minus, the interpretation of a negative exponent comes from negative exponent relates to adding and subtracting of exponents.
I gotta plug my computer.
Which is the rule. What do you call it? I'm going to write it. I am going to write it, even though you said no. X to the a plus b equals x to the a times x to the b. So when you multiply a bunch of a's, when you multiply a product of a x's by a product of b x's, you have a total of a plus b x's multiplied together. And that is what x to the a plus b is. So in the same fashion, we extend this rule.
Right. Yeah, you're right. We have to put the product rule in.
Yeah. Yeah. We extend that rule in this fashion. You could then see what has to be when a is the opposite sign of b. So in other words, a is minus b. Yeah. Sorry, when a is so x. Yeah. Now you take this and take a equals minus b.
Right.
So then you have x to the minus b times x to the b equals x to the minus b plus b, which is x to the 0. And x to the 0th, from this definition of x to the a, where a is a counting number, 0 is a counting number. Right. So you multiply with no x's, right?
Right.
Now, for this to make sense, so what must x to the 0th be?
1.
Why?
Why?
Because x to the 0 times x to the a should be x to the 0 plus a.
Right.
And in arithmetic, 0 plus a equals a.
Yeah, I've never seen it described that way.
So x to the 0 times x to the a should be x to the a.
Right, which makes
sense. And the number has the property that whenever you multiply it by another number, you get the other number back.
Right.
That's called the multiplicative identity. Right. This forces
x to the 0 to be 1.
Yeah.
So there's a common theme here. It's interesting. By the way, in math, you want to try to look for common themes. In fact, not only in math, in life, you want to look for common themes. Interesting. I never realized this before. What's going on here is that the exponent rules rule, and then the little funny things like x to the 0 and some of these other things are consequences of the exponent rule.
Yes.
So that these things are fudged. X to the 0 is fudged so that the exponent rules work.
Yeah. Yeah. Yeah.
Interesting.
Well,
Interesting.
so what I wanted to tell people to take away
Yeah.
is that an excellent way to remember these rules for exponentiation is to use the rules that come out obviously when the exponents are counting numbers. In
Right.
other words, x to the a is a x's multiplied together.
Yeah.
And from that, from the notion that x to the a is a x's multiplied together, you get both. See, can I scribble on the right hand side with the flower?
Why don't we take out this, okay? People by now, hopefully, everyone trusts the power rule, and we'll
Yeah,
give you more space. How about that? A nice, clean blue trapezoid thing.
yeah. So what was it?
How does that look?
Yeah,
Pretty good.
yeah,
Oops.
yeah.
Goodbye,
So
trapezoid.
so the rules to the rules are,
Oh, we're
yeah,
gonna summarize the rules.
yeah. X
Good
to the
idea.
a plus b equals x to the a times x to the b,
Right. And it
and
goes both
x
ways.
to the a times b equals x to the a raised to the bth power.
Right.
Both of these are consequences of, I'll write out both of them. X to the a plus b equals x times
Now,
x.
Seth, you already did that. You don't have to write them out, please.
I'm revealing. It's important,
Okay. But nobody ever does this. We should
and I do it.
summarize.
I do it.
We should
You add
summarize.
the a's and b's, and then x to the a times b equals x a times x a times
X A times
with
and
the
then B times.
parentheses is b.
Right. Okay. Good.
So if you have this picture in your mind, that exponentiation is multiply out the base the number of times given by the exponent.
Right.
And then that will lead you to remember that if you adding exponents means that you have x the base multiplied first by the first exponent number of times given by first exponent multiplied number of times given by second, and so you get the sum, and you get x's like that.
Right.
And
Okay.
then if you have when the exponent is a product, then the whole exponentiation result is the result of multiplying together with these things in parentheses, which are each multiplying x by itself the same number of times.
Okay, now we have all the exponent rules laid out, everything there, everything's in front of you now. We got all the exponent rules. And not a bad idea if you get confused with exponent rules is just do a few examples. And that'll help you. Okay. Yeah, I guess we have to do that, right? X to the 2/3, right? Is 4. X cube root of 2. Cube root of 2. 2. No, 8. 8. What am I doing? It's getting late. We have to move on. 8 to the 2/3 is the cube root of 8 to the second power. And x to the negative 3 is 1 over x cubed. X squared times x cubed is x to the 5th. X squared to the cube power is x to the 6th. Okay, are we done?
2 times 5 is 10.
Damn it. Damn it. Damn it. Damn it. Damn it.
Yeah.
Damn it. Thanks, Seth. That's why.
Well, one of
no, that
a
was
value.
3.
Why do math? Why bother? Why do math? One reason for doing math.
It's a 3, Seth. I wrote it as a 3. I just didn't look at that. It was actually
yes. Okay, so when you do math, you develop the skill. You develop the skill and the power to combine, things with rules with great care, precision, without making mistakes.
Right.
And so practicing math makes you do many things that require putting things in place. With much better. Like, for example, say if you're you're covering your floor with tiles, you want to put the things just in the right place. Well, that is the kind of skill that you get from doing math.
Yeah.
Okay.
Okay, so today's Wednesday, but we're going to do Throwback Thursday. Sometimes we move Throwback Thursday to another day. Today, so what is Throwback Thursday? Throwback Thursday, in around 2016, the SAT people changed the way they do their tests. They took it a little bit away from an IQ, reasoning, intelligence test, and made it more like just testing you what you learned in school. So let's every once a week we go back to a test from maybe 20 years ago and see how it feels different. So here we go. We're going back 20 years from the SAT review book. So here we go. Oops. There we go. This is Now we gotta clear the screen, right? Clear annotation. Wall drawings. And here we have a question from a review book. Here it is. Official SAT book. Wow, look at that. So old school. Now, Seth, this is a question that is basically what's called combinatorics. I actually never learned it. I'm learning it. I've picked up a lot of it. So Seth and I talked about, I never saw the question yet. I'm going to struggle with this thing like most people would. And then when I get in, I'm going to give myself 3 minutes. And in 3 minutes, if I don't get this done, then Seth's going to come in and go over how to do it. And even if I get it done, Seth's going to say, hey, you could have done it this way. Okay, so I'm starting the time now. Now I'm going to annotate in Zoom as opposed to Whiteboard. And I'm going to give myself a nice green color. No, let's do black because it'll show up better. Okay, ready? It is now on the time, 38:34. I'm going to go 4 minutes. No, 3 minutes. Let's go. There are 3 roads from Plattsville to Ocean Heights and 4 roads from Ocean Heights to Bay Cove. If Martina drives from Plattsville to Bay Cove, oh God, are you kidding me? If Martina drives from Plattsville to Bay Cove, so this is Martina, and back, passes through Ocean Heights in both directions. Well, why didn't they say that in the first place? Oh, God. And does not travel any road twice. Are you kidding me? Well, this would never be on the 2016 test. How many different routes of this trip are possible? Wait, and doesn't travel on any road twice. So, You've already got it. Okay, fine. So there are three. She has. I'm gonna just maybe. I'm not. I'm gonna try three choices. There are three choices going this way, right? So we have three choices. Usually that thing about the sandwich problem. You know, how many sandwiches does it? How many sandwiches can you make with a bunch of different choices of bread and filling? You multiply the choices. So I have three choices there. Now I have four choices here, so I can multiply by 4. So there are 12 ways to get to there by going this way. Now, we can't go through any road twice. Does that mean that coming back, you only have 3 choices? I don't know if I'm doing this right. Seth will tell me. If wow, I am. It's a miracle. Wow, look, I'm actually thinking. So there are only 3. Oh, now I have my confidence. Thank you, Seth. Which means now there are only 2 choices coming back this way. My God, am I actually going to get this right? 12 times 6 is 72? Was my thinking? So this is what I would call it in probability a slot problem, and that you multiply the number of choices to get the total number of choices. Essentially a glorified sandwich problem. But you have different bread and filling, and how many breads can you make? How many sandwiches can you make? You just multiply the choices of breads and fillings. So Seth, did I do this right?
Yes.
How about my approach? Was my approach
Excellent
correct?
approach, yeah. Yeah.
Wow. So this is great, because I never back in the 70s and when I went to school, I have a PhD in PhD in engineering, in mechanical engineering. I never even took a class in anything which even taught me what the probability of rolling a 6 is on a dice. I never took any probability in my life. I just picked this all up recently. So therefore you can learn things. You can learn things even if you didn't learn them in school. Wow.
Yeah.
Wow. And by the way, Seth's been instrumental in helping me learn this stuff. Seth has a PhD in math, and I think your field was sort of related to this, right?
Yeah.
Yeah, so I've learned well from you, Seth. Thank you. Wow.
Yeah.
So it's a slot.
Yeah.
Wow.
So it's is where the choices made later are conditioned on choices made earlier.
Right.
But the problem is easier because even though the menu of choices at each stage of the trip depends upon the choices made earlier, the number of choices in each menu is the same, and therefore you could
what do you
count
mean
the total choice sequence by multiplying the number of choices at each menu.
What is a menu, Seth?
Well, I'll tell you the menu. When you start out, you face a menu of 3 choices.
Oh, that's
the first menu.
Wait. Menu, is that a technical?
It's not a technical term, no.
Okay.
And then, when you get to Ocean City, you face a second menu with 4 choices.
Got it.
You pick one of those choices. Then you get to B. When you're at B, you face the third menu. What is the third menu? The third menu is all 4 of the roads except for the one road that you had already taken.
Right.
And so the third menu depends upon the choice that was made in the second menu.
Wow.
Now, but the simplifying feature of the situation is that in the third menu, no matter which of the 4 choices were made in the second menu, the number of choices in the third menu is the same number. It's 3.
Right.
And then finally, when you get back to O, you face the fourth menu. That menu depends upon the choice. The fourth menu depends upon the choice that you had made from the first menu.
Right.
However, the third menu there are always two choices.
Right.
Right?
Yeah, wow. I mean, the way I like to do probability questions is categorize them as to the type of question. There were only maybe at the high school level, lower high school level, only maybe 6 or 7 probability questions. And one of these is what's called the slot problem. This is also considered, I would think this is the sandwich problem, where the number of sandwiches you can make with the number of choices as you multiply the number of choices of each choice. Of each type, like the bread and the meat. Yeah. So this is yeah. Wow. Great. Okay.
Well, I'm surprised and disappointed.
Yeah.
That they didn't include the distractor of 3 times 4 times 3 times 4.
Really? They didn't?
Nope.
That's interesting. Notice the other thing about probability is that you would never think that there were actually 72 possible roads. You would say, maybe 5 or 6, Intuition very often fails you in probability questions. Counting questions. Right? You can't, intuition sort of out the window unless you have the intuition that you have that Seth would have after years and years and years of doing these problems. Wow, I guess that's it, right?
Yeah.
Oh, by the way, we should feel good. Let's try. Oops. We never got a chance. Ooh, that's not good. Where is it? Oh. We should maybe see if we got the question right. Check answer.
Well, again,
yes, we got it right.
I think that we have convinced ourselves that we got it right.
Yeah, I know, but it's nice.
So we're not seeing if we got it right. We are looking at what the review book writers wrote for their answer and their explanation.
And then notice that with Khan, it's very nice. Even if you get it right, you could look at their explanation. Oh, let's quickly look at that. So we can simplify the explanation. So you have to know rational exponents. We recall that. Wow, look at that. I did it the same way they did it. Oh my goodness. Wow, look at that. My God. The way we did it, the way I did it was exactly the way they did it. Pretty cool. Or maybe not so cool. Okay. And by the way, with Khan, it's very nice. If you want it, you can watch a video. Talks about how to do the problem. See if it's some sort
Which of the following values is equal?
So anyway, so you can always go back with Khan and watch a little video on how to do a.
It's a different problem.
Yeah, it's a different problem, but it's a 2-minute and 33-second video on how to do basic examples. So that's nice. They give this all to you for free. So I guess next week we'll pick another one up. Maybe one of these. Maybe nonlinear equation graphs. Ooh, look at that.
Yeah, let's do that.
We'll do that on next week. Okay.
Okay, should we see what the review book said about the question we just did?
We just did.
No, the one with the counting of the roots.
No, Seth. No, this is from the book.
Oh, okay.
Oh, yeah.
So we don't have the Throwback Thursday question. We don't have an explanation that someone else wrote.
I mean, I have to look back at the answers.
Okay.
It'll take us time. It'll take time. So I don't think so.
Okay.
I mean, I have to go back to the answers to this thing. Yeah.
Nah, don't bother.
Don't bother. Exactly. Don't bother. Okay, everyone. Yeah. Have a great day. Today was a long video, but we went over all the exponent rules. So when we start doing more exponent questions, which at some point we will not go over the exponent rules again, although who knows, maybe 2 months from now we will. But the exponent rules are really important in order for you to do exponent problems. You can't do exponent problems without knowing the exponent rules. You just can't do it. Typically, I find that when people have the exponent test in algebra, Algebra 1, essentially ninth grade math, many people really do very poorly on the exponent rule test because it's intimidating. To a certain extent, when you're first learning them, they all may all the rules look the same, or all the exponent things look the same, and you got to figure out which rule it is. So it's typically a one of the more difficult tests out there during in the regular school year. Okay, everyone, enough. More than enough.
Well, the exponent rules derive from, counting of, mathematical operations.
Okay.
I
think
about prior in more elementary rules derive from counting things in real life, and mathematical operations are abstractions of counting things in real life. And then in exponentiation, we're not counting things in real life, but we're counting of mathematical operations.
Oh, I see. So in other words, it takes a while to develop the confidence and the intuition to do exponents.
That's yeah. So you have to get so familiar with the multiplication or counting things in real life, and then you count multiplications.
Oh, right. Got it. Yeah. So it's a little harder conceptually.
Yeah, so it's exponentiation doesn't occur in low level everyday counting.
Got it. It's not part of our intuitive life.
It's not part of our intuitive life. Yeah, so in the same way, you mentioned many videos ago about the lack of intuition that many people have about exponential growth.
Right. Yeah.
Is it rare that you actually experience it?
Well, it's not when you get strep throat. It's not. When you get strep throat, all of a sudden your throat, you feel okay, and then 3 hours later, you have this massively painful throat because the bacteria has going to go this way. Bacteria is not like that. Yeah. Okay, everyone. So have a great day. We've completely overdone it today. Have a great day, and we'll see you next time we meet. Please give us comments at satmathquestionoftheday@gmail.com, and please email us your SAT math questions at satmathquestionoftheday@gmail.com. Okay, everyone, have a great day. Bye.